so that they're not roaming around, scratching, barking. Hold on, I gotta put my headphones on. There, can I hear you?
I can hear you.
Oh, I went live.
Oh,
Can you hear
thanks
me?
for the warning.
Yeah,
Yeah,
no
I
warning.
can hear you.
Okay, good. Yeah, no, sorry. Did I neglect to mention that I was going to put that live? Yeah, we're live.
I'm really glad that, yeah.
No problem.
Warning.
No, there's no warning. There's no warning. We're doing it live.
Okay.
Have you got anything else to do?
Me?
Yeah.
Or
Yeah, any tweeting to do? Any?
I'm still sharing things out on Google Plus and sniffling a lot.
Okay.
Because sniffling is what I do today. Welcome to fall in the
I've
world.
resisted the haunting possibility that I have allergies, and so Carla gave me half of an allergy med because I was like, and pretty sniffly, and she's like, here, why don't you just try this? And like I try it, and I'm like, oh, and then I totally dried up, and everything was better. In fact, I should have done some today, so it's pretty funny. So I'm like,
Yeah.
I don't have allergies. I don't. It's just a cold. No. It's allergies.
The sooner you admit to a problem, the sooner you can fix the problem.
Yeah. Well, then I can just decide. I can do a tactic. I'm like, today I'm gonna, because it really does sort of dry you out.
Mm-hmm.
I'm not a huge fan of taking allergy medicine, so I just have to decide if I want to gross people out or not.
Yeah, I kind of have the choice. I can live, or I can not take allergy medicine and suffer horribly.
Yeah. Well, I see some people, so there we go.
15 viewers.
I'm going to say hi to a bunch of people joining us on this non-standard day. But there's good reasons, right? You're going to go and visit Brian Coberline and team tomorrow.
And yesterday I was out at Illinois College giving a talk there. So this is the week when I give talks everywhere because I can.
Good. I'm going to say hi to Jim Meeker and Richard Strassel and Nancy Graziano and Stephen Walker and Thomas Traniker and James Gibbs, Rick Schwartz, Hewlett Avron, Jill Sabrin, Nancy Graziano, Stephen Walker, and Guido Bibra, Michael Jobin. Hello, everybody. And for those of you who have no idea what it is that you've stumbled into, this is a episode of Astronomy Cast. Today we're going to do the standard model, which I'm amazed that we hadn't done that one yet. Was that in the list of suggestions, or?
It was.
Oh, okay. All right. Yeah. I mean, every now and then I'll sit down and brainstorm for half an hour, and throw in 50 suggestions for stories. And then Pamela will, either choose from that list or, whatever concept is sort of rolling in her brain at the time or whatever's kind of hot, she'll go after that. And so I guess this one had been around for a long time, and you've decided we'd finally tackle it. So we've kind of been around. We've talked about supersymmetry. We've talked about the strong force. We've talked about the weak force. We've talked about electromagnetism. We've talked about every aspect of the spectrum. We've talked about antimatter. So, we've talked about gravity.
It's just time to talk about particles.
Time to bring it all together. Yeah. Cool. I'm just reading here in the comments. Some people are saying there's some issues.
Your audio is cutting in and out.
Yeah, weird.
Do you have bad internet today?
I feel like I didn't reboot.
Do you need to reboot?
How bad is the audio?
Right now you sound okay. A couple minutes ago you were hard to understand because
things were cutting out.
Yeah.
Should be fine. I'm not running anything on the computer. I don't want to reboot it.
Dropbox.
Yeah, no, that's all off.
Okay.
I just don't want to. I don't want to have to go back in and get it started up. So,
and you.
I'm definitely getting there. I'm definitely getting the.
Don't move. If you don't move, I think we'll be better off.
And talk. If I move and talk.
So now you're fine. It's being persnickety.
Yeah, no, it just did it too. But I don't know whether it's the computer, whether it's upstream, anything. I don't know. Because I have really fast internet. Like I've got 100 megabits down. So there's something somewhere.
This is sadly what's going up.
Yes. Let's just do the show. and because, the local copy will get recorded to my computer and that'll sound great. But I'm not running Dropbox. I'm not running Google Drive. I'm not running anything. There's no kids in the house streaming their YouTube videos. So let's just do this thing.
Okay.
Tell me when you are ready-ish.
I'm ready to press record once I switch it to mono. Are you ready for me to press record?
Yep.
I am pressing record and it is recording. Hello, Preston.
Hey, Preston.
Preston, this is a friendly reminder. You need to put in the ad that hopefully will be saved in Dropbox for Clean Coders. Bob Martin's Clean Coders is the ad you're supposed to have, not the other Bob Martin one, because he's awesome and does too many things.
Okay. Thanks, Preston. Okay, here we go. Astronomy Cast, episode 392, The Standard Model. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Great. I would like to remind everybody that we actually record Astronomy Cast as a live show. So if you enjoy Astronomy Cast and you feel like, man, I wish I could hear Fraser and Pamela chat before they start recording the show and make a lot of mistakes with their audio and try to set things up and mess their intros, that would be cool. And also I'd love to stick around and chat with them and suggest topics and have some of my questions and have them answer it live and interact. And you can also do that. So we stick around after we record the show and answer questions for half an hour. So every Astronomy Cast is actually an hour long, but you as a podcast listener only get half of it. So you can join us live on YouTube. We post like literally everywhere. We post in our Twitter feed. We post it on Universe Today. So if you want to join us live, we do that every Monday at noon.
Except for today, which is Tuesday.
Except for today, we do often change the date. So just a reminder that if you want to join us live, we would love to have you join us and say hi and give us some questions, and we'd love to answer them. All right, let's get rolling. So physicists have finally come to realize how everything is mostly connected, how electromagnetism, the strong and weak nuclear forces, are really just aspects of the same thing, what all the particles are and how they interact. This is known as the Standard Model, and it's the theory that gives us our best understanding of the underlying laws of nature, except for gravity. Don't worry about gravity. Pay no attention to the gravity. Pamela, so the Standard Model, when you introduce the Standard Model in your classes, how do you sort of typically bring that up?
See, I'm lucky I teach the intro to physics classes, and so I don't have to go there. It makes it quite simple. In my universe, there are electrons and protons and neutrons, and we avoid everything else other than the photons.
And they're just like little solar systems with little atoms zipping around in little circles. Where you go a little
not quite, because I do address the fact that electron orbitals are not these perfect little ellipses like planetary orbitals, but rather are clouds of probability of this is where an electron should be. But yeah, we get to have it much more simplistic at the introductory level, which is really Newton's physics with a little bit of Einstein thrown in, but none of this quantum mechanics.
But when you fill in for the physics teacher who's handling, for example, the Standard Model, I mean, do you start by just telling everybody in the class that their whole life is a lie, that everything they thought was true is not true, that what they think is matter, and what they think is photons, and what they think is all connected in ways they could barely even imagine?
No, because that would be mean. And the reality is the Standard Model doesn't break any of our basic understandings of physics. The Standard Model is out there as basically a framework that you can plug all of the known particles into. And conveniently enough, it doesn't require anything we haven't discovered. And while there are a few things that should exist that don't seem to fit into the existing standard model very well, like dark matter.
Gravity.
Well, yes, gravity is sitting off to the side going, hello, I'm something else.
Yeah. What about gravity?
But for the most part, the standard model is that good, solid framework for putting together literally all the little bits and pieces of our universe within one conceptual understanding. And there's something highly pleasing about it because it's this beautifully symmetric, diagrammed out theory where you have different generations of particles of increasing mass and decreasing stability as you go, and there's symmetry where you have the electron and the electron neutrino and the muon and the electron and the muon neutrino, and all of these symmetries and all of these ways that things beautifully mirror across the different ways of having charge, of having color, of having all the different characteristics of particles. It's just pleasing. It's a pleasing theory.
I can just imagine what it must have been like when scientists, as they were doing the math and realized that you could sort of like pull out pieces and replace them, and it all started to come together into one big mathematical formula, and that you're just looking at the different objects in different ways. So what is then the standard model? What is sort of your definition when you explain it to people?
Well, the standard model, most simplistically, is the way that we organize the standard particles that make up our universe. It's how we look at the way up and down quarks add up to make electrons that have their partner, the electron neutrino, and they also work together to build the proton. And so out of these two quarks, we're able to get at all the stable things that make up our everyday interactions, that you have charm and strange that add up to build the muon, and then you have the muon neutrino. Sorry, up and down do not build the electron, they build the proton, but they're part of the family with the electron. And charm and strange are part of the family with the muon. And we just have these beautiful symmetries as we go through. And then you end up with bosons as well that are another set of partner particles. And these are the ones that carry the force that hold together these particles in all of these different ways. And it's literally just a framework, and we plug the things into the framework and the math works out. And the displeasing part of it is, while it's like a puzzle that comes beautifully packaged, that you dump it out on the table and you put everything together and it fits, just like there's absolutely no reason that one puzzle should have the Hobbit on it and another puzzle should have the Mona Lisa, there's absolutely no reason that this particular puzzle should shape out our universe. It is filled with a bazillion, by which I mean a few dozen, constants that are just kind of, the universe said this is what the constant should be.
Right.
And
alpha is this.
Yeah. So there's a whole lot of the universe simply says this is what it should be that we can't mathematically explain. And that makes a lot of people really uncomfortable. They want there to be an underlying, these masses must have these values because of this underlying physics, and these things must have these constants because of this underlying physics. And the standard model is like, nope, I'm good.
Right. Here's the part where you multiply everything by 1.0296418. Because that's the math. Yeah. So then let's go top down. So let's look at like we know that houses and trees and cars and stuff are made of molecules.
Yes.
And the molecules are made of atoms.
Yes. And
the atoms are made of?
They are made up of things called leptons. So this is where we have electrons, are the stable ones that show up in atoms. And outside of the atom, we also find muons and tau particles that crop up. And these are all part of that lepton family. And mediating a lot of these interactions are their partner neutrinos, the electron, muon, and tau neutrinos. So that's that first order of stable particles
Right. So when I think of like we think of the proton and the neutron in the nucleus, and we think of the electrons in this probability shell around the. Now you can't break the electron down any further, right?
No.
It's
So
a particle.
the electron, the muon, and the tau particle are just fine the way they are.
Right.
And so are their matching neutrinos.
Right. And so you've got in the center of the atom, you've got that nucleus, you've got the protons and the neutrons in whatever configuration. And those can then be made up of smaller particles, right?
Yes, those are made up of the quarks. And in particular, everything, again, with the symmetry of all the stable stuff falls into the first generation of particles. Those protons and neutrons are both made up of the up and down quarks. So we have up and down quarks make up the protons and the neutrons. And then in that same first generation, we have the electrons that orbit that nucleus made of protons and neutrons. And mediating the interactions, we have the electron neutrino and its antiparticle, the anti-electron neutrino.
Now, when you say mediating those interactions, what does that mean?
Well, so for instance, we have the decay process by which a neutron, if you try and leave it out on a shelf all by itself, it will decide, I would rather be a proton and an electron.
Because who wouldn't?
Exactly. Everyone wants to be excited with charge, and a neutron's just not excited with charge. And so the process by which it changes its identity from being that neutron to being a proton and electron, you have to conserve all the little bits. And part of conserving all the little bits is you have an anti-electron neutrino that goes off and is taking care of things that otherwise wouldn't be properly conserved.
And so are these, I mean, when I think about these particles, I kind of imagine them, they are the thing that carry, that provide these interactions. But you imagine them kind of like zipping back and forth, or like, how are they actually doing this, or do we not even know?
So the quarks are held together depending on what it is that's being built. They're being held together in groups of 3 or 2, or we think 5 now. That we think there might be some pentaquarks out there.
Right.
And they're held together in some cases with what are called gluons. And so inside the atom, we have those protons and neutrons are held together with gluons. And so we talk about the gluon boson, and we did an entire show on forces and bosons. The gluons are gluing the quarks together to form these particles.
Now, is there anything that we know of that's even more fundamental? Do we know if there's anything that makes up quarks?
No. In fact, quarks should be, unless our theory is totally foobarred, quarks should be the fundamental particle.
And so there's nothing that makes up quarks unless you're a string theorist, and then you think it's vibrating strings, but we're not going to go there. Okay, so then how do the forces, right? So those are the particles. How do the forces play into this? The strong force, the weak force, and electromagnetism.
Well, it depends on exactly what the particle is. So the gluons, this is the boson that is basically holding together the quarks, and so this is part of the strong force, and the way we look at it is this is one of the stronger forces, thus called the strong force. That was a bad unintended pun that came out there. And so quarks are held together with gluons. It's a strong force. It's mediated by the boson when you start looking at the mathematics. Then you have the electrons, and the protons most of the time are just acting like happy little charged particles. This is how electronics works. This is how we deal with a lot of things in everyday chemical reactions. And all of these electromagnetic forces are said to be mediated by the photon, which is another type of boson that we also talk about as being light. So those are really the two big ones that I think we worry about on a day-to-day basis. We also have the electromagnetic force. This is where we start looking at the W and Z bosons that are mediating that. Again, we did an entire show on this.
Yeah, on photons.
Yeah. So there's a lot of little particles, but everything lines up so that we have the weak force mediated by the W and Z bosons, the electromagnetic force mediated by the photon, the strong force is mediated by the gluon. Where things go sideways, as you already mentioned, is with gravity. And a particle that currently sits outside of the standard model and may or may not exist is the graviton. So we have a word, but it hasn't been observed. And like I said, it sits outside of this standard model that we've put together.
Quantum mechanics describes with tremendous accuracy the movement interactions of all of these particles. But when you try to bring in gravity, if you try to take gravity and you try to take some of the math that works just perfect for quantum mechanics and use that in gravity, what happens?
Well, we just don't have a theory. So if you try it,
you get infinities.
Well, it's sort of like saying it's the color 6. It's if you don't
can't get there from here.
Yeah, exactly.
Yeah.
Or the sum of 2 and 2 is blue. There may be a theory for that, but we haven't found it yet.
Right. So now, what about antimatter? You know, how does antimatter play into the standard model?
Well, it's generally just it's the complementary particles where everything was formed with symmetry, although due to asymmetries in how things decayed in the early universe, we did end up with mostly what we refer to as regular matter instead of antimatter. Regular matter and antimatter, they both have positive masses. It's the exact same mass generally, but you end up with other differences. So the positron, which is the antimatter particle of the electron, has the opposite charge. So some of the characteristics of the antimatter particles get flipped. And because of this flipping, when the matter and antimatter particles meet, it tends to be rather explosive. Now, this isn't to say that every time antimatter hits regular matter, you're going to get an explosion, because there are plenty of antimatter particles flying through you right now. It has to be the right type of interaction. So a positron and an electron that meet are going to annihilate one another and become a happy little burst of energy, or an unhappy burst of energy. But that antimatter neutrino that's flying through your body right now, your body doesn't care.
So, I mean, we know that the matter and antimatter, all of the different forces today, all of the particles, they're all separate, discrete things. They interact with each other, but they're their own thing. But I think the part that's kind of most amazing to me is how cosmologists have gone back in time, right to moments, with their math, right to moments before the Big Bang, and really started to figure out how these elements, or how these different forces came together in a more fundamental way, and when you're like right at the edge, right moments after the Big Bang, we didn't have this separation the way we do today.
Right. As near as theorists can tell, as the energy within a volume increases, the way the forces act starts to become more and more unified. As the energy goes up, the first thing that you see happens is the electromagnetic and the weak force become the single electroweak force.
The electroweak force.
It's a thing.
And so you can take the math for electromagnetism and kind of plug it into the weak force and make one set of math that describes that, when it's in a hot, dense state.
A better way to look at it is, as the energy density goes up and up and up, the way these two forces work becomes the same thing.
Right, I see. Okay.
So it's not that you're plugging one into the other, it's that within the limits of the way the universe was in the first moments, both the forces are acting the exact same way and they become the same force.
And I guess why did they separate is a weird, but I mean, that's
well, that then becomes, as the energy density goes down, their behaviors differ. And we can think of this in a lot of different ways. It's a mathematical limit. So when we use Newtonian gravity, it describes everyday life perfectly well, and it doesn't have all of those extra bits and pieces that relativity has. But if we used the relativistic equations to describe everyday life, those terms are so tiny that we get the exact same results. Now, the electromagnetic and the weak forces do have different ways of existing in the low energy regime. But as you get to higher and higher energies, it's just the equations tend towards the exact same place.
right. Okay. And so then the same thing happens with the strong force.
So at an even higher energy density, at an even earlier point in the very beginning of the universe, the strong force then merges in with the electroweak force. And if you keep going back, if you keep going to higher and higher energy densities, as you get to earlier and earlier times in that tiniest fraction of a second after the Big Bang, gravity should merge in as well. Now there, we're still working on the math.
Right. And that is still, so that sort of leads into my next question, which is, what are the big unknowns in the standard model right now? Where, I mean, we just, by we, I mean they, and by they, I mean, Nobel Prize winning physicists just added the Higgs boson, which was sort of like one of the final big pieces of the standard model. So what is still left to discover?
The way you're describing it makes it seem like we've known about the standard model for a bazillion years, and the Higgs boson is just something that came out of left field. And the reality is the standard model is something that's largely been worked on since World War II. This is largely new physics that required particle accelerations, colliders to do the experiments that led us to understand, well, there's a whole lot more than just the proton, electron, and neutron to this universe we live in. And in the wild heyday of coming up with all of these particle physics theories, the Higgs boson was theorized fairly early on. A lot of this work took place in the 60s and 70s. Now, the problem was that while all 6 flavors of quarks had been predicted for decades, and the Higgs boson had been predicted for decades, in order to create the high density of energy in one point that would allow these higher mass particles to spontaneously come into existence out of the energy, we had to build massive supercolliders. And it's only been with the Tevatron at Fermi and the Large Hadron Collider at CERN that we've finally been able to generate the needed energies to have these particles spontaneously come into existence out of the energy. So Higgs is a new fabulous measurement of something that the standard model had been predicting since before either of us were born.
Right, but I guess if that particle hadn't been found, it would have meant there was something seriously wrong with the standard model itself.
Yes.
But by finding it, it really makes the standard model even more almost bulletproof at this point. But yet there are still other places, right, where it goes.
And so where the standard model leaves us going, is dark matter. So there's a particle called the axion that isn't required by the standard model, but fits within the schema of the standard model that might help us solve the dark matter problem. It could account for 85% of the dark matter out there. So the standard model doesn't leave us high and dry with dark matter, but there's a lot of other ways of theorizing dark matter that require entirely new additions to the standard model. So you have supersymmetry, which ends up with each particle being just one of a giant family of particles. Dark energy also really doesn't fit within anything. Dark energy is kind of that reality that makes everyone scratch their heads hard enough that sometimes their brains really are going to fall out, because we don't know how to get there from here.
Right. So it's not just gravity anymore that cause these problems for the standard model. There's, as you said, there's the dark matter, there's the dark energy. Dark matter maybe fits within, but that's still, it's like they have to keep pushing. And we did a whole episode on supersymmetry. And in fact, we actually did 2 episodes on supersymmetry. We did one and then threw it out because we weren't happy with how well we were explaining it. And then we did a whole other episode. So, and so when you listen to our supersymmetry episode, that's actually our second take on the entire episode. We literally got 95% of the way through and said, you know what, this is just garbage.
I think we've, in all the 400-ish episodes that we've done, we've only done that 3 times.
Yeah. And earlier on, and that was the one. I remember that as the one. But anyway, so we did a whole episode on supersymmetry, and it really is it's like the Higgs boson, if I remember right. The Higgs boson is like the bottom of the ladder, and supersymmetry is this whole new ladder, and the rungs just go, but they're just going to take higher and higher energy to get anywhere near them to confirm dark matter.
And it starts to feel like a ladder that was built by Escher.
What do you mean by that?
So Escher paintings where things fit together in all sorts of strange branching ways. Supersymmetry starts to feel like you go up one ladder and find yourself at the side of a different ladder in a different dimension.
Right. And it's got to be frustrating for the particle physicists because, or maybe it's exciting, I guess, because they've got, at this point, right, the standard model is so complete. And so, as you said, you take all the puzzle pieces, you throw them on the table, you put it all together, and you're like, look at that. It's like a perfect circle. It all works great. And then you're like, but what about the dark matter? Where does that go? It doesn't even fit in. And the gravity is like some kind of goo that how does that come together? Right.
Well, so like I said, the graviton doesn't break the standard model. It's just not something we've been able to observe. And the axion may be an answer to dark matter, and it doesn't break standard model. It's just not required. The real issue that I think we come down to with the standard model is there's a lot of people that just are like, this must be wrong. And the reason that, and wrong in the sense that, like, Kepler's theories of planetary motions described everything perfectly, but they had no underlying physics. And a lot of people are uncomfortable with the standard model because it has all of these constants in it that are just sort of measured and not predicted or anything else. So people really want that beautiful, elegant underlying theory that says, well, we have all of these constants because of this thing, and these are all derived from this resonance. And standard model just is. It just is. And as an observer, I'm good with that. I'm good with having a universe that is sometimes at the most simple level just built that way and needs a constant now and then.
Right.
But it does leave people looking for that underlying perfect singular unifying theory very uncomfortable.
Right. But if there were no mysteries, they would be bored, right? So, I think it's the searching for it is I think what keeps them entertained, as not necessarily finding it. I'm sure that's exciting, but you want to have another mystery around the corner. Unfortunately, the universe has no shortage of mysteries around the corner.
That's entirely true. And while the standard model may be the Kepler's theory of planetary motions of the particle physics world with no underlying, well, because this, just like Kepler's theories were beautiful in describing how planets moved until you got to Mercury and required relativity. The standard model works. And that's a starting point. That's a starting point to being able to build and do and eventually understand. So we'll hopefully get there.
Great. Yeah. And if, I guess, what's next? What is the sort of the cutting edge research or the theoretical work that's being done. Like if there was some like buzzwords, I mean, people have heard string theory, but that's only just one. What are some other kind of terminologies and stuff that people might have heard that where people are trying to sort of search for, I guess, the Einstein, the relativity's version compared against, you know, Newtonian motion? What is the sort of next class of theory that people are trying to explore?
I think that supersymmetry is really the place where people are currently trying to figure out, is this theory real? And this, again, gets back to the building the bigger detector, because if we can get to higher and higher energies, we start to be able to produce some of the lower mass supersymmetric particles that are still just out of reach of what we can do. And there's been some tantalizing hints that maybe we're starting to get, but the data is still really noisy. It's like trying to watch a channel you don't legally get on cable television. You sometimes get hints that there's a signal there, but most of the time you just get static. So we need to get to those higher energies to start to prove with meaningful signal whether or not this additional suite of particles exists. If it does, that starts to get us at an underlying theory. But it's still a start, and we're still missing gravity. So the standard model continues to be, even with supersymmetry, a theory of mostly everything, but not yet everything.
Awesome. All right. Well, thanks, Pamela.
Thank you. Saving.
Yeah. So get your questions ready, everybody. And then I got to remember to turn my dropbacks back on.
Yeah. So Sky and Telescope just tweeted this very amusing result of image search, where they image searched on Castor, and apparently there's a mammal beaver called Castor, and so they posted an entire page of happy fuzzy wood-eating, tail-thumping beaver pictures. So Sky and Telescope, you amuse me greatly.
We have beavers near here.
Yeah, so do we.
Yeah,
I've never
so
actually seen them. I've just seen what they've done to the fallen trees.
Yeah. They dam up nearby rivers and turn them into lakes.
Yeah.
Okay, so let's look at some questions here. So Thomas Traniker says, I love how Fraser says Traniker. It sounds so much better in English. How do I say it then? Is it Tranaker? What does the A with a little circle on top mean? I don't know what the pronunciation for that is.
Yeah,
so,
I don't know A with the little circle.
Little circle on top. So if you want to let us know, that would be awesome. Nancy Graziano. But then if you like it better, then then don't tell me, and I will just continue to give it, you know, in my Canadian accent.
I see Nancy's post, and Nancy, I have a feeling they have me running like a crazy person the entire time. But if you want to pass on recommendations for food and other to Brian and I'm sure it would go greatly appreciated.
So Nancy also says, quick reminder that this Saturday is Space and Astronomy Day in New Jersey, sponsored by the New Jersey Astronomical Association. Special guests are Morgan Renberg and Kimberly Cartier. So go to astronomynj.com/Nov14, so like November 14th. So, but I'm sure if you go to astronomynj.com, there'll be more information there. And if not, Nancy is fixing it madly, which is great. Morgan and Kimberly together talking about planetary and exoplanets. That'd be awesome.
So Ed Thompson's asking, Pamela and Fraser, do you ever have an open house or get together for Astronomy Cast fans to meet you? Yes, we do randomly. Mm-hmm. It all depends on where we are. So for instance, I do things here in the Edwardsville area, but most people don't live in the middle of the country. So when either of us are at big events, we try to do meetups. I think the next one that either of us will be doing is I'll be at the American Geophysical Union meeting in San Francisco the week of December 15th, and I will be doing a meetup. I just haven't posted it yet. So that will probably be the Thursday night of that week that I'll do that.
And then we typically are at DragonCon every year, every second year.
Yeah.
So if you want a chance to see us and a whole pile of your favorite people, DragonCon is one of the best places to come and hang out with us.
And I'm going to go to a region in Boston this year to feel it out and see how that con is, because it's my home city and it's a winter con and I'm tired of sweating in costumes.
Right. I can't get out of the country right now so much, although I do still, but because my my now wife is working on her immigration, and so she can't leave too often while we sort of get this whole thing, because she might not be able to be allowed back in. So, but once we're done that, then I would hope to do a lot of travel and do, I think the other big thing we're thinking of is we're going to try and figure out something special for the eclipse in 2017. Yes. As I've mentioned.
And we are going to be working with our favorite composer, who I know is out there listening, David, said something in the feed. Let me see if I can find what he said. Scrolling. So David Joseph Wesley, he just said howdy in the feed, but we are going to be working to get you music to fulfill your music desires.
Really?
Yes.
Oh, that's awesome. That's great. So for anyone who doesn't know, what I want, my greatest dream is I want someone to compose a symphony to be played live during an eclipse, so that you could watch the eclipse and people could be playing the music. I think it'd be awesome. And then people could just, play that at different eclipses around the world. Okay. What else have we got? So Ed Thompson asks, in your opinion, what is the most intriguing concept theory within the Standard Model? If you wanted to really grab a person's interest or make them go, whoa, you blew my mind, and only had time to describe one concept or theory, which one would you pick?
One of my favorite things is muons are formed in the upper atmosphere, and they're moving so fast that relativistic time dilation occurs. And while the amount of time that it takes them to travel from the top of the atmosphere to the bottom of the atmosphere should be long enough for them to decay, that relativistic time dilation means that we're able to detect muons at the surface of the Earth.
That's crazy.
Yeah, so
they
that
should have decayed. They should have decayed, yes, but they're going so fast that from their perspective, they haven't decayed.
Yes, and thus we detect them at the surface of the planet. You can do this in most undergraduate physics labs, and a lot of museums have muon detectors.
Yeah, I think my favorite is just, how we talked about how in the earliest times of the universe, how these forces are indistinguishable from each other, how they all come together, electroweak, and then they become what's the name for all of them sort of together? The strong and the weak and the electromagnetism are all looking like the same thing, which is just super interesting to me. But that muon one is great. Yeah, we talked about that we did a whole episode on
time dilation.
Well, with time dilation, we did one on there's a special class of observatories that just detect
gamma ray detectors.
Yeah.
But Shrenko?
Yeah, Cherenkov radiation. Yeah, Cherenkov radiation. Yeah. I think we did a whole episode on Cherenkov radiation, which is super interesting. Let's see. Richard wants to remind you, Richard Drum, the astronomy bum. This show will be uploaded to 365 Days of Astronomy on Monday the 16th. Do you want to get a recap? That's the way to do it. Free on iTunes, of course. James Gibbs says, in the movie The Martian, and maybe also the book, I've not read it.
Read it. It's awesome.
Yes,
Sorry.
Absolutely. You should read it. And also the audiobook is terrific.
Yeah.
Mark Watson makes extensive use of duct tape. Do astronauts actually take duct tape with them to space? If so, how much has it ever actually been used in space?
It's been used. I don't know how much, but yeah, they have duct tape. It's it's a thing. You need duct tape.
Yeah. We've seen from Mythbusters, right? The Mythbusters survived on a desert island with only duct tape. Thomas Traniker says, raining diamond on gas giants, that screwed with my mind. So we've heard that, right? Yeah. Raining diamonds. Yeah, it's a thing. You're gonna have to deal with it. Get used to it. It's reality. How do the diamonds rain on gas giants?
I don't remember. I have to relook that one up every time.
The forces are ludicrous.
Well, yes.
And that's what you get. Richard Drum says, Ed Thompson, you may want to come to DragonCon next summer. Both Fraser and Pamela will be there. Fun times. Yeah. Pamela, you're going to be at DragonCon next year? Yeah. You've already got your hotel booked?
Yeah.
I am 91% planning to attend.
Oh, INS. It's so much fun. See, I get to laugh because I went through this exact same thing 9 years ago with my husband, who's Canadian and in the United States, where we couldn't leave the US.
Yeah.
So there's just symmetry here with the time delay.
Yeah, we did. Actually, Carl and I went to DragonCon last year. So not the summer we just had, but the year before, which was great. She loved it. She's a huge sci-fi nerd. So, let's see. Oh, hold on. There was another one here. Yeah, Richard Drum also says that Apollo 13 used duct tape to good effect, which that's what I remember. They've had that table. Like, here's what they've got to work with, and of course, duct tape. Come on. Eli Davron says, I have no questions today, so I'll just shout out to Paul M. Sutter's Ask a Spaceman podcast, which I've been listening to lately, and it's really awesome, so give it a try. Mad props to Paul M. Sutter, one of the panelists now he was our special guest on the Weekly Space Hangout, and now is a regular panelist, and invited Pamela and I to get to OSU to hang out with them and give some talks, and yeah, great. He's a smart guy. He's a rising star. Keep an eye on that guy. Let's see. Guido Bieber asks, mid-type question for Pamela. What are the plans for Learning Space? You said something about bi-monthly in the last episode. You meant bi-weekly. Is Learning Space up tomorrow? What's happening with Learning Space?
So Learning Space this month got kind of sideways because I got killed with NASA paperwork. We
in the good way, right?
In a good way, but it hammered me in the back of the head and carried me down a dark alley and then shook all of my budgetary skills out of me and left me drained and dying on the sidewalk. At least that's how it felt.
Super brutal, Pamela.
It was the paperwork really tried to break me. So anyways, Learning Space was supposed to happen last week, but like I said, I got carried down a dark alley and beat up by NASA paperwork. It will be not this week because I'm going to be at RIT, but next week and the week after. So we're going to have 2 episodes for November. We try to always have 2 episodes. We're just doing them back to back this month because I had fail. We're going to have special guests, Travis Rector, Kim Cowell, I think Meg Watson or Wozniak is also joining us. These are the folks behind the From Earth to the Universe and the Hubble Heritage and a bunch of other amazing imaging programs. And they're going to come on and talk about how amazing astrophotography is created with both the Backyard Telescope and the Hubble Space Telescope. So join in and learn all about image repositories where you can get your hands on your own images and try this out. And I still need to line up the rest of the semester.
That sounds fantastic.
I love NASA. I hate paperwork.
But thanks for the money, NASA.
I will be hiring someone to help me with the paperwork so there's less beatings that occur.
Yeah. And Mike Vogel asks, will there be another show on black hole physics or expansion related topics anytime soon? That's one of the problems with the way we do Astronomy Cast, right? Like, we do an episode on black holes at like episode 12 or something, and then we do supermassive black holes, then we're done.
So it might be time. So we're about to do a whole series on standard model stuff. So today was kind of the intro and overview, and then we're going to go into each of the families of particles. But after that, it might make sense to start looking at things that have symmetries at different scales. So looking at stellar mass black holes, supermassive black holes, and the jets that are associated with them at both sides. And one of the reasons I mentioned that is there was one of the worst headlines forever, and it was used like on a bazillion different websites, and it was black hole spits out material, and black holes do not spit out material. They
Black hole
really
accretion
don't.
disk. I actually did an
Yes.
episode. Yeah, I did an episode for the Guide to Space called "How Do Black Holes Shine," and that was the gist of it, right?
And so it might make sense to do something on either how that title gets misused or something to try and clear that up, because it hurts my soul when people start talking about black holes spitting things out.
So Ice Colden says that the letter A with a little circle on top, which I'm sure has a name, especially in Scandinavian languages, is said the way O is said in O. So it would be Tranoker, Thomas Tranoker. Now, does it still sound great, Thomas, or now is it ruining it for you? We were at the museum this weekend in Victoria, and they've got this Aboriginal peoples exhibit, and they have like hello said in all of these different dialects in British Columbia, and then they give you this sort of language guide on how to, how to pronounce all of the word sounds that we don't have. And there's about 12 word sounds, and the symbols are really strange, and they have no connection, like they're a click or a sh sound or a t. Like there's these sounds that we just don't have. It's pretty interesting to sort of, when you run across those, right?
So I saw, and then my screen scrolled and I lost it. There it is. So Tom Van Scooter, I'm not sure how you say that, points out that duct tape was used on the moon to repair a fender on the lunar rover on Apollo 17. And that's cool.
Hussein Ali says that on 511 said he found no evidence of alien signal on the alien megastructure star. Could we trust SETI's result? I mean, is it accurate? There's 1,400 light years between us. Could we be accurate? So
it's a first order result. That means that they aren't encrypting things using the cosmic microwave background. Or rather, it means that they could still be encrypting things with the cosmic microwave background, and we're just not noticing it above the background. It could be that they're only doing direct line of sight communications. It could mean that they're communicating in completely different wavelengths.
Or they're just not beaming any signals, in our direction, right? Like,
exactly.
That to actually pick up a communication that's 1,400 light years away, it has to be sent in a directed collimated beam at a target. If you're just, if they're just talking and sending out radio waves in all directions, we're not going to be sensitive enough to pick that up. They've got to be actually saying, hey, Earthlings, here's our message. So, and across the spectrum, like there's so many variables. I mean, it would have been a total Hail Mary to actually catch a signal from this star the first time around. It doesn't mean they're not there, and it doesn't mean that they're there.
It just means they aren't wasting electricity on us.
Right. Or they're probably a smashed up planet or cloud of comets, which is, the much more likely result of what this is.
We don't know that. We don't know what's most likely.
Comets exist around other stars.
Right, but they don't exist in swarms like this would have to be. So we actually don't know what's more likely. And I know that hurts your soul, but we don't know what's more likely.
How is this that you've been the one who won't rule out aliens while I'm the one who's being skeptical about this? Is we're just like we flipped our X-Files personalities here?
I simply am saying that the statistics do not allow you to make the claim you are making.
All right, fine. Because my imagination can go anywhere. My imagination can take over here. Okay, well, I think we've got all that wrapped up. So I don't know if you see any other questions. Has anyone tweeted at you?
No.
Anything else we want to talk about? Any other business we should get people to do? No? Well, have a solemn and memorable. You guys have Memorial Day tomorrow, right? We have
Yeah, we do.
Remembrance Day. Yeah.
Yeah, we just have Memorial Day.
Yeah.
So
11, 11, 11, 11.
yeah. So poppies to all of you from nations where that is part of the tradition, and say thank you to a soldier, because
Absolutely.
all around the world they've helped protect all of our nations.
Okay.
So thank
All
you.
right. Well, thanks again, Pamela. Thanks everybody for watching. If you haven't already, subscribe to this channel, which is specifically the Astronomy Cast channel. So make sure you subscribe to it, and that way, you know, previous episodes will show up whenever you go to YouTube. Like, subscribe, give us some feedback on iTunes if you want to rate the show, and then also go and do the other things. Go to CosmoQuest and do some science. Go to Universe Today and enjoy some space news, and especially subscribe to my YouTube channel, which is just do a search for Fraser Cain. You'll find it. Cool. Well, thanks everybody for watching. Pamela, thanks as always for joining us. This begins a whole new series, so I can't wait to figure out what we're going to talk about next week.
Sounds great.
Thanks, everyone.
Bye-bye.